Hello and welcome. Today I'll show you a demo and then an explanation of the CPU that I made in Virtual Circuit Board, and that is a digital logic sim. So first I'll give you a quick demo of the program that it can run, which will be drawing a circle on this virtual screen here. Then I will quickly explain how the simulator works for those that want to know. I'll try to add timestamps so that you can skip it if you're not interested. Then I'll give an explanation of some of the individual components and then an explanation of some of the architectural decisions I made. And then finally we'll take a look at the assembly for the program. Okay, so now I'll give a really quick explanation of the simulator. So there's obviously wires in the simulator to transmit signals. So this is a wire and this is a wire. This is just an on-off signal that I can turn on by hand. And then this is a write block. That means that this object is writing to this line, and these three are reading from it. Same with this one. This is writing to it, these three are reading from it. Then you have gates. So this is an AND gate, this is an OR gate, and this is an XOR gate. As you can see, when both signals are off, they're all off. If I turn one on, the OR and the XOR turn on. If I turn both on, the AND and the OR turn on, but the XOR, of course, turns off again. Another thing is there are these buses that can transmit multiple signals up to 16. So as you can see, as I turn on different bits, the bits are also turned on the output side because the bus carries them. And you see a bunch of those lines here. This is a bus. These are buses. Without that, the screen would be completely cluttered with lines everywhere. Then, I'll explain some of the components of the computer. The ones that I'll explain will be the program counter. We'll also talk a little bit about the instruction register there. Then, the register file, the ALU, the control module, and the memory, of course. So, okay, the program counter. The program counter is really just a memory address for the next instruction, and whatever value is in the program counter will be sent to the memory bus, and then the memory that is at that address will get read and sent into the instruction register. Then, after the program counter, there is also the adder here, which will add 1 to whatever is in the program counter, and that will be stored in the program counter again. That'll happen every clock cycle, so that every clock cycle we get the next instruction, instead of just running one instruction over and over again, which would be useless. That value that comes out of the adder actually doesn't get sent into the program counter immediately. It goes through this, which is a multiplexer, and that is in case we want to do a jump or branch instruction. We of course would not just want to do the next instruction, we want to jump somewhere else, a different address. So that's all there is to say about the program counter. Next up is the register file. The register file at the computer is of course inspired by MIPS, so there are around 30 registers because MIPS has 32 registers. However, there are some registers that are not used. So for example, the 0 register always holds 0, so in reality we can just not have it exist in the hardware. There's also some other registers like 26 and 27 that are used for things that I didn't need, so I just left them out. Apart from that, the register file is just a bunch of registers, and each register is a 32-bit short-term memory thing. Data can be read from it or written to it. And we have one write bus here and two read buses. These buses are all connected to every single register. Now, we only want to write to one register at a time, or we want one bus to read from one register at a time, which is why we have this register control module up here. The read A module will decode a part of the instruction and tell one of the registers to output its value onto the read A bus. Same for read B, it will tell one register to output its value onto the read B bus. And finally, the write module will tell one register to overwrite its value with whatever is on the write bus. Finally, what is on the write bus is controlled by this multiplexer here, and it has data coming from the ALU, from memory, and from one other place, I don't remember, and it picks which one to put on the write bus. Then we have the ALU. This is the ALU, this is the actual part of the ALU that does all the calculations. So it has two input buses where it gets its two 32-bit input values from, and then there are a bunch of functions that it can do, and you have this little control module on top of it which selects which operation to apply on the inputs. So for example, and, adding, subtracting, ORing, or I think there's also shifts instructions that it can do. There are also two output bits, that's these two lines here, that detect specific conditions for branch instructions, and they are sent over here, and they will determine if a branch is taken or not. Finally, there's this bit here which is for immediate value padding, to make sure that you can have negative immediate values and positive immediate values. Then we have the control module, which is here, and the control module takes 6 bits of the instruction, namely the opcode, and decodes it. That's this part. So every unique combination of those 6 bits will turn on one of these specific lines, right? That's a decoder. And then each of those lines will be encoded again into control signals. So here is a control signal table, and each opcode or each instruction requires certain control signals to be on or off when the instruction is being ran. And this table is basically embodied by this encoder, and as you can see, these control signals are sent all over the computer. Finally, we have the memory. We have the address here that is 20 bits long, and that simply takes an address, and then the corresponding memory will be available to read or write to here in this part. The memory in this game is virtual. You could make your own memory, but I decided not to for reasons we'll get into in a little bit. So, then we'll get into the architecture. First of all, there is one memory bus. Initially, I wanted to make a Harvard architecture computer, which means you have one memory bus for the instructions and one for data. However, the game only offers one virtual memory, and making your own memory is possible. However, that would slow the simulation down, and it would be less memory. And there's a few other reasons, like it needs to work with the screen and the assembly, which is why I decided to use the virtual memory. So then it becomes a von Neumann architecture, or von Neumann architecture, or however you say that. Which means that there's one memory bus, which means that the loading of instructions needs to share the memory with the program. So, how do you do this? You can only access the memory once per clock cycle. So therefore, I needed to pipeline the CPU a little bit. I did not go overboard with 5 stages immediately. That would be far too much work. So I went with 2 pipeline stages. Which one is which? Well, the first pipeline stage is simply the program counter increasing and loading the next instruction into the instruction register. That's all. The second phase is doing the instruction, basically. The instruction gets pulled from the instruction register and sent through the control module, the ALU, the register file, etc. The instruction is executed. And once again, it's pipeline. So in the meantime, the next instruction is being loaded. But this is not all. This creates some problems, because only one of the stages can use the memory at a time, because once again, you can only have one memory interaction per clock cycle. So you would not be able to load an instruction and store a piece of data in memory in the same clock cycle. So what I do instead is, if there is a read-write instruction, read or write instruction, in stage 2, then the control module hands control over the memory to the second stage, which means that the program counter's value will not be put into the address. You'll see there's a multiplexer here that selects between the program counter or some other part, I think the ALU. There's another thing it does, namely it stalls the program counter. There's actually, the way I add 1 to the program counter every time is I turn on or off the carry in the adder that comes after it. So if there is a memory instruction in the second stage of the pipeline, I will turn off the carry in, meaning that 1 will not be added to the program counter. Whatever is in the program counter will be stored into the program counter again. So it stalls for 1 instruction. On top of that, a no-op will be loaded into the instruction register, because if we do, for example, a write to data, and we read whatever is at that memory address, that is not supposed to be an instruction. If we load that into the instruction register, we will get a trash instruction that could mess up the entire program. So that is all as far as read and write memory instructions go. However, there are also branch and jump instructions, which also interact with the program counter. And we only know that there is a branch or jump instruction in the second stage of the pipeline, because this is where the instruction gets unpacked. So if there is a branch or jump instruction, then this multiplexer here will take the value of whatever address you need to go to and put it in the program counter instead of program counter +1. On top of that, whatever instruction is being loaded here will be killed. Because say you have a branch instruction, you have your if statement, and then you jump, right? Because the if statement isn't successful, let's say. So you jump behind it. You don't want the instruction that comes 1 line after the if statement to still be executed. But sometimes you do. This is actually a design decision, because if you don't execute it, that's a wasted clock cycle. If you do execute it, it is not. However, the programmer needs to fit in an instruction after the if statement that will be always ran. So I chose not to do that because it's more annoying with programming, but it can save you a clock cycle every now and then. So apart from that, there's also this diagram I made while I was making the computer, and this shows all the data paths and which control signals need to go where, and this just helped me while I was making it. You can see this on the GitHub, which I'll link in the description. One more thing, I did not make an instruction specification, which I should have done, but oh well. Let's go on to the assembly. So, the way the assembly works is each line of code in the assembly editor is interpreted as a 4-byte value, and each line will be stored in memory consecutively, and once again each line will occupy 4 bytes or 32 bits. It is up to the hardware to interpret this as instructions. It is just numbers in memory. So, for example, this origin 0x0001 means that from here the program starts, and every line of code after this will be stored as an instruction in memory as a value in memory consecutively, and it will start at address 1. So you could write your program as just integers like they used to do with punch cards, but that would be a pain, so let's not. So what does it offer? Well, it offers symbols, which means that you can say symbol RV1, which stands for register V1, is 3. So now whenever I type RV1 in a line of code, it gets interpreted as 3. So we can already start to do things with this. On top of that, everything in one line of code gets ORed together. But this is not enough, because what if we want to say add two numbers together? We want to say add whatever is in this register, whatever is in that register, and store it in that register. But if we just say, okay, I want RT1 and RT2 to be added together, then these will be in the same line, so 9 and 10 will be ORed together, which creates 11, which is meaningless. So that's why you have macros. So you have add, we have the opcode ORed together with parameter A, which will be bit shifted into the correct bits, parameter B, so that's you add these two together and store it in register C. And all these registers will be bit shifted into the correct 5 bits. And the hardware will know how to read that out of the instruction. So the instructions we have defined here are no op, which does nothing, addition, subtraction, ANDing, ORing, XORing, NOR, shift left, shift right, move, that means you can move something from one register to the other. You'll see that the opcode is the same as addition. That's because secretly this is just addition, but we're not adding anything. Immediate instructions, so add immediate, AND immediate, OR immediate, XOR immediate, just putting an immediate value in a register. Once again, this is the same as add immediate. That's a trick. The hardware doesn't actually have to know what an immediate instruction is. We could just define it. We have branch instructions, so branch equals, branch greater than 0, branch less than or equal to 0, branch not equals. Store word and load word is for interacting with memory. Jump, jump and link, jump register, jump and link register, and these are all for functions. So let's take a look at the circle render program. We're not actually going to go through the whole program. I'm just going to show you an example of the multiply function, because we will need multiplication, but the hardware does not have a multiplication function, because that would make the clock cycle time way slower. So instead I programmed it with like addition and shift left and whatever. We'll get into that. Let's find an example. So here we can see jump and link multiply. Jump and link is just calling a function, right? The way you give parameters is by storing data in specific registers. So for the multiply function, whatever we want to multiply, we need to store one number in A0 and the other in A1, and these two will be multiplied together. And the result will be stored in register V0. And there's also our register A2, which is used for the maximum amount of bits. That's an optimization. You could also just assume that you always need to multiply 32-bit numbers. However, if the numbers are shorter than that, then you're multiplying a bunch of zeros in the end, which wastes a lot of cycles. So I chose to do this optimization. So we store two numbers. In this case, we square whatever is in register S5. So we store register S5 in RA0 and in RA1. So you can see we use a move instruction for that. Then I know in this case that the numbers will never exceed 6 bits. So we will add an immediate value into register A2, namely 6. So we've given the function its parameters. Now we can actually jump and link to the multiply function. So here is the multiply function. The first thing we do is we store some immediate values, namely we store 1 in register T1 and we store 0 in register V0. Now remember, V0 is going to be the return value. So we first set it to 0, and that is because we will do the multiplication in a loop, and every loop we will add to V0. So we want to make sure that there is 0 in V0, because otherwise we would add to whatever number is already in there, which would screw up the multiplication. After that, we enter into a loop. The first thing we do is we AND RA1, which is the multiplier, with 1. And we store it in a different register, namely T2. So what does that mean? That means that we basically mask out all other bits except for the first bit. Then we check if that is equal to 0. So we're basically checking, is the first bit of the multiplier 1 or 0? If it is 0, because we check if it's equal to 0, then we branch and we jump ahead one instruction. So we skip this instruction. If it is 1, then we do this instruction, and what we do is we add the multiplicand to the result. After that, and whether we skip it or not, we do these instructions. So what we do is we shift the multiplicand left and the multiplier right. Then we subtract 1 from RA2, which is the amount of bits that need to be multiplied. So we know that once this hits 0, we will have multiplied all the bits. In this case, we will do this 6 times because we put 6 into RA2. And this branch checks if we should continue the loop or break out of the loop based on if this has reached 0 or not. So this loop will run 6 times, in the case of this function call, of course. And then it will simply do the same thing. Now, I'll explain this function a bit better in a second. After all of that, we jump register RA, which is the return address, so the code jumps back to here. After the multiply function, it just continues with whatever code is there. And now the result will be stored in register V0. That's how the multiply works. Now, I'll explain this function a bit better. What I want you to do is open Paint or grab a piece of paper and first take 2 random 4-bit numbers and do binary addition. Write them on top of each other and add them together. You should know how to do this. Now, to do multiplication, what you want to do is you want to write the multiplicand, and it doesn't matter which one is the multiplicand, which one is the multiplier, just pick one to be the multiplicand. Write the multiplicand Then write the multiplicand again, but under it, and shift it 1 bit to the left. Repeat this 2 more times, and then you should have the multiplicand 4 times, all diagonally under each other. Then write the multiplier next to it vertically, and write the least significant bit at the top. Now cross out each row where the bit of the multiplier is 0. Finally, add together all the remaining rows, and then you have done binary multiplication, and this is essentially the algorithm that this code runs. That's really all. So, bye.